Okay, so now I'm going to listen to Anthony Leverrier, who is going to speak about Bosonic code, so these interesting gate sets.
Thank you, Nicolas. So I would like to thank the organizers for inviting me to give this talk. This is a Bosonic code session, so we'll talk a bit about Bosonic code, and also because the context in which I've looked at these questions was really the context of Bosonic codes. But the talk will be also about standard qubit codes. So most of what I will be explaining is based on this preprint that we have with my student Aurélie Denis. This is the preprint is mostly about Bosonic codes. But if you don't like or if you don't care about Bosonic codes, here is a natural problem that you may want to think about. This is really the problem that I want to explain today. So the problem is as follows. So I have some logical group of gates that I want to apply to some system, quantum system, a logical system. So typically, if I have a qubit, this could be like a subgroup of SU2. Okay, so this is the set of gates I want to apply on the logical system. So that's the first ingredient. The second ingredient is that I want to give a representation of that group, a physical representation of the group. Okay, I want to say, okay, so maybe this is the single qubit Clifford group, and I want to say that each of the gates in this group, I want to apply them with some transversal implementation. If I have qubits, or if I have a Bosonic code, maybe I want to apply them with Gaussian unitaries, or whatever. So you have really two inputs to my problem. I have a logical group of gates I want to do, and I have a representation of these gates. And then the question I ask is, can you design a code where the logical gates are implemented with this physical representation? Okay, so this seems like a very natural problem that should have been asked many times, many years ago, probably. Maybe people have thought about that. I don't know of any paper that formulates it like this. If you know of one, please let me know, because I think it's a well-posed problem. So, and then, yeah, that's a different question. Yeah. So this is for qubits, but if you have, Bosonic codes, you have no distance, so really you want some kind of protection. Okay, so yeah, so in the next 10 minutes, we'll talk about Bosonic codes and where this comes from. But if you really don't care about Bosonic codes, try to think about this. Okay, so what's the story of this result? So the initial idea was to do something that Victor mentions, was really to design multimode Bosonic codes, Bosonic CAD codes. And we tried with my student for a long time, for more than 1 year, to try to do something, for 2 modes. In the end, we found something, not a qubit, but like a logical qubit. It's okay, it's not great, but we managed to publish it thanks to our viewers. And then a few months later, Victor and Sasha and their students, they came up with a very broad generalization of this thing, this quantum spherical codes. Basically, killed the question of what do you find, multimode Bosonic encodings. Nice properties. And so then what happens is, okay, maybe you should switch the question. So maybe not look for codes which have, nice error protection properties, but maybe focus more on, nice logical gates. Can you find codes with nice logical gates? So in that part, I will talk about, Bosonic codes with this kind of gates, and then I will extend this to general codes. Okay, so first part, so it's really about, the multimode Bosonic case. So the starting point of this work was really to say, okay, most of the Bosonic codes that are studied, they are single mode. You have CAD codes, GKP, square GKP, hexagonal GKP, binary codes, many things. So if you have only a single mode, most of the things have been studied. It's not clear you can find new, very smart single mode encodings. So what about multimode encodings? In theory, they should give better performance, better protection against noise. So to simplify the problem a little bit, we chose to look at encodings where the code words, the logical code words, they are superposition of coherent states. Okay, you want to say, okay, my logical 0 is a superposition of coherent state, my logical 1 also. And then the question is really about finding a good constellation, in phase space. And the constellation that we wanted to look at are constellations with a nice group structure. So you have basically two choices. You can take an additive group structure, and you get basically a lattice, and you get, TKP codes. Or you can take a multiplicative group structure. And in this case, for single mode, you get, the constellation will be the roots of unity, and you get cat codes. And maybe you want to do something like this in more modes, so in more dimension. So really, this was a strategy. You pick a nice constellation, say in C2 if you have two modes, or in like a larger space if you have more modes. So if you pick a constellation of size n, you end up with an n-dimensional Hilbert space that is spanned by your n coherent states. And then the tricky part is to find, a good logical qubit or qubit or whatever in this space. Okay, so what we did was exactly this. So we picked, a nice constellation in C2. So it's a constellation of 24 states that corresponds to a binary tetrahedral group, which is called 2T. So it's a group. It's basically the polygroup plus Hadamard. So it's a group with 24 elements. And so if you pick this constellation, it defines a 24-dimensional subspace of the two-mode Fock space. And then the question is, how do you find a good code or a good qubit or qubit in this space? So there's a nice way you can use, you can do numerical optimization where you you optimize encoding and decoding of your code. And this can be done with SDPs. So this can be done efficiently. So you can try to do that to optimize numerically something. But in the end, you don't really get something. You get some random things that you cannot really exploit. In the end, we finally, managed to, we didn't find a good qubit, but we found a qubit that has nice properties, nice symmetry properties, and we call this the 2T qubit. So as I said, it's a okay qubit. It's not a great qubit. Still, let me show some plots. So these are, this is kind of a nice figure of merit that you can look at, is the fidelity of entanglement of your code for the pure loss channel. So you take a pure loss channel, as Victor explained, with some loss parameter gamma, and then you can look at the fidelity of entanglement of your code for this channel. So when the infidelity here, so what you want is a small number. And here, basically, what we do, so this green thing is a 2T qubit for different values of the loss parameter. And these other things, there are things that you can find when you start with a random encoding, and then you optimize with this, where you optimize encoding and decoding. So what we find is that the 2T qubit is a fixed point of this optimization, so it's a local optimum, and it's pretty competitive if you have low loss. Okay, so it's okay. Here we did basically the same thing, where we compared the 2T qubit to various single mode qubits, cat qubits. And the 2T qubit, the blue one, this is as a function of alpha, as a function of the energy of the constellation. So there's a sweet spot. And again, this code is not too bad. Okay, it's okay. It's not great, but it's okay. But it has an additional feature, this code, is that it admits some nice logical gates. And this is really because of the group structure that we use. Okay, and then a few months after we had our preprint out, Victor, Sasha, Shubham, and Joseph, they came up with this very broad generalization called quantum spherical codes, where basically the idea is to do kind of the same thing, but you replace the group 2T by some spherical designs. And when you do that, you get very nice protection because of the symmetry of these things. And they can also work with some logical gates. And in this paper, so they have like tons of codes that they find. There's even a variant of the 2T Qubit, but with better performance against loss. This was a bit depressing that this guy, they came up with this very big generalization and they improve on the single code that we had. And then I was trying to figure out the differences between their code and our code. And what happens is that our code has a slightly more bigger set of nice logical operations that you can do. And then this led us to, to ask a new question. Okay, so can we design Bosonic codes that have a lot of nice logical gates? In general, you can also say, can you design arbitrary codes which have a nice set of logical gates? And what I want to say, what I want to explain in the rest of the talk is that the answer is yes, and there's a very systematic construction to do that. This should be known, but again, I didn't find it anywhere. So what's the general idea? So usually what people do when they study quantum codes, they really first, design a good quantum code with some good parameters, good rate, good distance. This is the first step. You design your code. And then what you try to do is to, understand how you can perform gates fault tolerantly. Okay, what kind of gates you can do with your code. And here the approach is completely opposite. First, we want to find a code family. So code is with, quotes, because again, it's not necessarily a code that will have a good distance, but we want to find a code family which has nice logical gates. This is really the first thing that we ask. And this I will explain, this is easy to do. It's very systematic, there's a systematic way of doing this. And then, once you have this, then you try to optimize. And within this construction, so you get a full family of codes like this, you try to find the codes which have good code distance or good tolerance to noise. And in general, this is the tricky part. Okay, so what's the setup of the problem? As I mentioned at the beginning, so if you were not interested in Bosonic codes, you can come back now, because here it's the very general statement. So what you want, the ingredients that you're given, so you're given a group of logical gates. So say if you have a single logical qubit, you want a subgroup of SU2, maybe you want all of SU2. And then what you're also given is a nice physical representation of that group on the physical Hilbert space. Okay, so a representation rho. So again, rho can be like a transversal representation. So rho of G would just be G tensor n. It can be a Gaussian unitary if you have Bosonic code. It can be whatever you want. And then what you want to find is an encoding map, and it goes from the logical space, so C2 if you have a qubit, to your physical Hilbert space that has this property. So that should be covariant with respect to the group action. So what you want is that E is the encoding, so you want that if you encode G applied to psi, so G is an element of this group on C2, on SU2, you want this. So this is the encoding of the state, the logical state after you applied this logical operation. You want this to be the same thing as applying rho of G on the encoded state psi. Okay, so this is what you ask. You ask this for all elements G of the group. So that's the game. That's what you want to do. And what's maybe surprising, maybe not, I don't know, is that this is always possible. There's a very simple general construction that gives you all of these guys, all of these encoding maps. And now the main open question is really how to find within all these maps that you get, or do you find the ones which give you good protection against noise? Okay, so there has been previous work on similar questions. Not that many that I'm aware of. Probably the one that really started this kind of line of research was Jonathan Gross, where he was considering encoding a logical qubit into a spin, physical spin. Then more recently, there are students or postdocs with Victor, Eric Kubista, and Ayan Teixeira, where they looked at similar questions but they consider qubit codes with transversal gates. So rho of G would be just transversal gates in that case. And there are also works where people looked at codes with continuous symmetries. So apologies if I'm missing some references. If you know any other work on these things, please let me know. I would be curious. Okay, so what's the general recipe? So I told you that there's a very general way to get a code with this kind of group covariance. So what is it? So again, so the ingredients are the logical group G, the nice physical representation and a physical Hilbert space, so rho. And then you can pick two other things. So you can pick any logical state of CD, so some state sigma. You can pick it arbitrarily. And you can pick any physical state in your physical Hilbert space. So if you, for instance, if you look at Bosonic codes, you might want to pick the vacuum state or a coherent state. So these two things, you choose them as you want, these two states. And then you can define an encoding map that looks like this. So it's a bit scary at first, but you know, it's a sum over the elements of the groups. So it's a superposition of states. So which are the states? So the states are so you basically you apply your physical representation, rho of G, on this physical state that you started, that you chose. So this would be states, and this bracket is just, you know, complex coefficient. It's the amplitude that you should choose for your superposition, and the amplitude is given by this thing. And what I claim is that if you do this mapping, this encoding map, it will have the property that I want. So in some cases, you need something a little bit more general. For instance, if you want to recover GKP codes or CAD codes, CAD-qubit codes, you may want to consider a group that is not directly a subgroup of SUD, but something bigger group. And then here, basically, what you want to replace this G here by the logical representation on SUD of that group. And you need a little bit of care if that representation is not irreducible. But okay, so that's the basic, the recipe. The recipe is this: you pick any physical state that you like, any logical state, and this gives you a code. Or this gives you an encoding that has the right, that has the property that if you apply a rho of G on your state, it will apply logical G on your logical state.
What's
Sigma L, sorry, it should be rho L.
Okay.
So it's the representation of the group on SUD. Okay, so to prove that this works, it's not too complicated. You need a few ingredients from representation theory. But these are really elementary facts of representation theory. What you need first is that if you have any representation of a group, you can always decompose it as a sum, or you can always write it as a sum of irreducible representation. So basically, when you have rho of G, there exists some unitary, in our case, because everything is unitary, so there exists a unitary U, such that rho of G is just the conjugate by U of this thing, and here we just have a direct sum of rho I of G. So rho I of G is one of the IREPs of the group G, acting on some space which is isomorphic to your logical space. And there's an identity operator applied on a multiplicity space of your IREP. So you can always write any representation like this. Then you need to know something about IREPs, about these elementary things. So basically, there's a kind of an orthogonality formula for IREPs. So if you take this kind of sum, so you sum over the group G of these two terms over IREPs I and J. So if I is different from J, you get 0. And otherwise, you get this kind of operator, which is just a swap gate between the two systems. You need the last thing, which is the what you project onto each of these elements in this decomposition onto this. These are called isotypic components of the reps, and there's a way to write down the projector onto that space. Okay, so these are the three things that you need. So these, again, these are elementary facts from representation theory. They are not complicated. And then with these things, we can try to understand the encoding map a little bit more precisely. So the encoding map was this thing. So basically, it takes some state psi in your logical space. You have this encoding map, and you get some encoded state in your physical space. So this map is just given by this thing, this big operator, and then you also input basically your physical state psi, phi, that you chose, and you will project onto the logical state sigma that you chose also. And then if you work out the math, it's not complicated, you can check that basically this map corresponds to this kind of circuit. So basically you have your physical state that you chose, phi, is projected onto the E-rep corresponding to the direction that you want. Then you have this unitary operator that acts on this thing. Basically, it will give you two subspaces at the output. One is isomorphic to your logical space. One is the multiplicity space. And then basically what you do is just you swap the state that lives in the logical state space that you want with this system. And you put that back in there, and you, again, apply U. And this is how you get this thing. Yeah?
Yeah, sorry, I can't work this out in real time, but is the idea that these encodings, like, would they be invariant under the action of any G in your chosen group set, or are they going to map to each other?
So the encoding, they satisfy the relation that I want. Well, they satisfy this thing.
So this is all you require.
So this is all, this is all I want.
But these, like the constructed code words don't satisfy any additional.
No, in general, no. Then if you want additional things, then you try to do that, to get that. So if you want to have distance, whatever, then you try to ask for that.
Gotcha. Okay.
But here I just want this. I just want a general recipe that gives me this.
Cool. Thank you.
And basically, all the maps that are of this form, they are necessarily of the form that I explained. So if you have a map that satisfies this, it's necessarily of the form that I gave. For some choice of these two things, of sigma and phi. Okay, so you have this kind of encoding circuit that you can write down. And then you can prove that the thing respects the symmetry that you want. So basically, what you want is that if you instead of starting with a state psi, you start with a state G applied to psi. So this is your logical state. Basically, the only thing that you need to check is that when G goes through this unitary, it gives you the right thing. And it does because of the way this thing is defined. So there's nothing really complicated. So maybe in real time it's not so easy, but it's just the proof is very simple. And then this proves exactly what I want. So it proves that the encoding of G of psi is always equal to rho of G applied to the encoding of psi. Okay, so there's another way to write the encoding map. So this thing is maybe a bit complicated. You have these three things. You have these two states, somehow that you don't understand. There's a nicer way to write it. It's basically you can say, okay, whatever I have in this part of the circuit, and that thing don't really matter. What really matters is what happens around this unitary U. Basically, on one input, you get psi, which is your logical input. And the other thing that you care about is what you put in the multiplicity space. Okay, so the other way to write this encoding map is really this thing. So the encoded state is just, you apply this U now on your logical state, and anything that you want in the multiplicity space. Okay, and for any state like this that you put in your multiplicity space, you get a code that satisfies the covariance condition that I want. Okay, so the codes that satisfy these relations, they're really in one-to-one correspondence with the state that live in this multiplicity space. Okay, so in general, this multiplicity space, it would be like C to something, so C2, C3, C4, whatever. So you have like a Hilbert space here, and you can choose any state that you want inside this thing. Any state will give you an encoding, and it will give you an encoding that has the covariance property that you want. And in this picture now, U is not acting on the full space here. It's just acting on this logical space and the multiplicity space of the rep that you care about. So really, U is an isometry from CD, your logical space, and your multiplicity space to the physical space. So it's an isometry that is given to you by the choice of the group G that you want, and by the choice of the representation, the physical representation that you chose. Okay, and now the game is a bit different from the standard thing. So now the game is really to find the states or the encodings that give you good protection against noise. Okay, so it's kind of not easy way, but this is what we have to do. Okay, so that's a very general recipe. Yes, please.
So you've shown how to code these states, and you can reach all of the states that you want by encoding different starting ones.
Yeah.
So once you're encoded, does this then guarantee that you can apply a logical operation that maps you between these?
Yeah.
What is the, like, if you want to apply the representative of G, then you apply U of G or something? Or
So if you want to apply the representative of G on this thing,
yeah,
you just apply rho of G. So rho of G can be transversal gate.
okay.
G tensor n can be Gaussian unitary, can be whatever you want. And this will automatically give you the encoding of G of psi.
Okay. And now you want to check if the states are protected against noise?
And now I want to check that.
Thank you. Sorry.
No, that's fine. Thanks for the question. Okay, so that's the general recipe, and now I want to show you some examples in the bosonic case, and then talk about qubits. So first, bosonic codes, because this is the application we had in mind at the beginning. So here, basically what we want to do, so rho of G, there are many choices, but the kind of natural choice for the representation is to take it's called the Gaussian unitary. So maybe you want to do this one. So G, it's a unitary matrix, and the rho of G will act on this coherent state, multimode coherent state, by mapping this coherent state alpha to some new coherent state G of alpha. So this is kind of the nice set of gates that you can think of. And for the states that you need to choose, so you need to choose a physical state. Kind of natural thing that you can do is to just pick a coherent state. So if you do that, what you get, the encoding will be a superposition of coherent states, because you start with some coherent state phi, and you apply some Gaussian unitary, so you get again a coherent state, and then you have this weird, amplitude that you should compute. But if you do that, the encodings, your encodings will be superpositions of coherent states. So they're kind of nice. So this kind of generalized, I don't know if they generalize, but I guess spherical codes are a specific example of this, where this thing is one, basically. What is kind of nice is that you can basically recover GKP, and you can recover the cat codes basically without doing anything. If you choose just the right group and you pick just a simple coherent state, you recover GKP and the cat code. And you can define new codes. So this is what I want to do now. So first example, GKP. How do you recover GKP? So what you want to do is you want to encode a qubit into a single mode Fock space. So what you do, I want for this code, for GKP, I need the simple generalization of the formula that I explained. So basically what you want to start with is this physical group. So you have a group that is generated by these two displacement operators, so displacement by alpha and displacement by beta in phase space. Don't really need to know what these are, but they satisfy this kind of condition. They anti-commute if you choose alpha and beta in the right way. So for instance, you recover the square lattice of GKP is the one that you get if you take alpha to be square root of pi over 2 and beta to be I times square root of pi over 2. So this would be your group. This is your group. And then you need to choose a logical representation, a two-dimensional representation of the group. And the way you do that is you say that you pick the representation that associates to d alpha, the sigma x, and that associates sigma z to displacement by beta. So this is just the poly group. And now what you do, you just pick, so you need to pick two states. You need to pick a logical state, so you just pick 0. You need to pick a physical state, you just pick the vacuum state. And if you do that, and so you have this formula that was given before, this is the encoding formula, where the sigma by state is 0, and the physical state is the vacuum state here. So you have this formal sum that you can compute. So you need to look at which are the non-zero elements of these things. And they only appear when rho L of G is plus or minus identity or plus or minus sigma Z. And then so you can work it out. And it's not very complicated. And you get that 0 is just a superposition onto a lattice of coherent states like this. And 1, you can get it also as a superposition of coherent states. So really, you recover GKP, the GKP code, without any fine tuning. You just choose, so I said in the recipe, you need to choose two states, logical state and a physical state. Here I just chose 0 for the logical state, the vacuum state for the physical state, and put that in the formula and then get GKP. You can also recover very easily the two n-legged cat qubits. Here what you do is the group that you pick, you just pick the cyclic group of order 2n. Again, you need the logical representation of that group, and you just need to explain what is the representation of the generator of that group. So you just say, okay, it's sigma x. You need a physical representation of that group, and you just use the very natural one, which is a dephasing operator by the same angle. And then you need to pick your two states. So again, you pick sigma equals 0. You pick phi, your physical state, to be a coherent state, an arbitrary one. And you can compute the thing, and you get the cat qubit. Again, without any fine tuning, you didn't need to really look for a code with the good properties. You take the simplest one that you can come up with, and you get the cat qubit encoding. So these are codes that you can recover easily. Now you can play with this formalism a little bit and to define new codes, new Bosonic codes. So for instance, codes in two modes. So what you can do, for instance, is you can pick your logical group to be in just the poly group, sigma x, sigma z, your Hilbert space to be the two-mode Fock space. And then you use the same Gaussian unitary representation as I explained before. So where the representation of this SU2 unitary is just given by this map. Maps coherent set alpha beta to something. These are operations that you can do with beam splitters and phase shift. And again, so you need to choose two states. So logical state, you can pick 0. You need to choose a physical state, you pick just a two-mode coherent state. And if you do that, what you get, the formula gives you these kind of things. So you get a code, and the basis of this code is just a cat code, an odd cat code in the first mode for the 0, and even cat code of amplitude beta for the second mode. And then to get 1, basically you just swap the two modes. Okay, so this encoding, so in the limit of, if you pick alpha and beta to be of the same amplitude, and if you take the limit alpha to 0, you recover the dual rail encoding. But in general, you get some kind of finite energy version of the dual Rayleigh encoding. And then here, I mean, there's some freedom. So I said that you choose some, you need to choose some initial state, alpha, beta. And depending on how you choose it, you can get different performances. So this is again, as before, the entanglement infidelity for a pure loss channel as a function of alpha. And this is for different values of alpha and beta that you choose. So there's one. So if you look at the value alpha equals 0, this is a dual Rayleigh encoding. But you see here that you can have codes with much better performance than the dual Rayleigh encoding. So here you need to optimize. You need to optimize your initial state. And the kind of the rule of thumb to do that is really to maximize the distance between the points of the constellation. Same as for quantum spherical codes. Okay, so you can do this. A more interesting example is this one. So you don't take G to be the single qubit poly group, you take it to be a single qubit Clifford group. So formally, it's called the binary octahedral group, 2O. It has 48 elements, and it's generated by these two matrices. And you can play the same game. So if you play the same game, now you get an encoding, a code where all the elements, all the single qubit Cliffords, they are done by Gaussian unitaries. And then you can, it's not too complicated to complete that with a, to get a universal gate set, to get C nodes or CZs and T gates. But here you need, it's not Gaussian unitaries anymore. It's like unitaries with quartic Hamiltonians. So it's a bit less easy, but if you do that, you get a universal gate set. So this code is easy to measure in a 0-1 basis. But state preparation and how you do error correction, it's not, I don't know how to do that. Okay, so that's just one other example of bosonic codes that you can do with this kind of machinery. Okay, so this was what I wanted to say for bosonic codes, and now I want to tell you about qubit codes or arbitrary non-bosonic codes, because the same formalism applies exactly in the same way. So if you, okay, so the construction is very general, so you can think of, you have a qubit for the logical space, so it can be one qubit, it can be many qubits in whatever dimension that you want. You have a physical space, which is also many qubits. And then you need to choose, you will have a group and you need to choose a physical representation for that group. So natural choice is just to choose, transversal gates. So you apply the same gate to all of the physical qubits. So you can use G tensor N or G dagger tensor N, or you can mix both. So you have many options that you can do. You can do other things. And also, so some examples. So if you, for instance, if you want a code where you encode k logical qubits into n logical qubits, and the group that you care about, the group of transversal gates that you want is just a poly group, and you want basically, or you want to apply, logical poly elements with physical poly gates, you can do that. And if you do that, so you can compute what I said before, the projector onto the rep. And basically, the projector that you get is just the identity. You get everything. So in that case, the multiplicity space that you get is of maximal dimension. So you really, in that case, you get the unitary that is doing the encoding. It's really a unitary, it's not in symmetry. And you can choose it to be a Clifford unitary. And you recover stabilizer codes like this. Okay, so this just gives you stabilizer codes. But no more interesting, if you look at, so this kind of approach, it works well for small codes. For large codes, it's not so clear how to do the computations, but for small codes, it works very well. So one example that you can try to do is to look at a code of 5 physical qubits where you encode 1 logical qubit. And maybe what you want to, the group of transversal operations that you want to do is the group 2T, the binary tetrahedral group that I mentioned before. So it's basically polys plus Hadamard. So if you want to do that, basically you need to choose an IREP, a two-dimensional IREP for that group. So there are 3 possible choices. So this would be the IREP for the logical space. So for instance, we pick the one called row 5 in the literature. This is just this IREP. So the element Z is mapped to this thing. This is basically a standard Z matrix, and this is Adam out. And then the physical gates I want are just transversal gates. Okay, I want to say that if I want to apply G in that group, I just apply it transversally on the 5 qubits. So now what I can do is I can decompose my representation, this row tensor 5, into a direct sum of E-reps, and I get these three things. And basically the code space that I want, if I want a code space where you have this property that the elements of 2T will be transversal, it will live into that E-rep. So you have row 5, and the multiplicity space associated to this is of dimension 6. Okay, so you really have that all the codes of length 5 that have transversal 2T, they are in one-to-one correspondence with states in C6. Okay, so for any state in C6, you get a code which has transversal 2T. And there's a choice, you can find it, where if you do that, you recover the 513 code. Okay, and so it exists, but it's not as, for the moment, it's not as clean as in the Bosonic case. In the Bosonic case, really the choices that you made for phi, it was really the obvious thing, and you would get the best code that people know. Here it's not so clear how to get phi. So you need to choose it carefully. At the moment, I don't have a complete recipe for how to find it. I'm kind of optimistic that there should be a way to do that. In particular, there's a kind of a canonical way to pick one state in this space. And if you do that, you almost recover this code, but not quite. Yeah, we'll talk about it a bit later. It will come. Okay, so this was for 5 qubits and the binary tetrahedral group. What you can do now is, you want to recover STEAM code. So you want a code with 7 physical qubits, and you want transversal Clifford group. Again, the group 2O as before, and you can do that. And so you have several representations, 2-dimensional representations of this group. You have 2 basically. Or you have 3, but you have 2 which are interesting. So you pick row 7, for instance. So the logical representation will be just row 7. The physical representation is just the tensor product of these things. So row 7 tensor 7. And when you do that, you get this kind of decomposition. So row 6 and row 7, they are E-reps of dimension 2. This is an E-rep of dimension, I think it's 4. It's not 8, it's 4. And basically, so if you just pick, row to be row 7 tensor 7, so if you put a dagger in that thing, you get STEAM code. And even if you don't put a dagger, you still get STEAM code, but with a different labeling. Here, what I don't tell you is that again, so now you have like a 15-dimensional Hilbert space where you can choose your state. You have a 15-dimensional Hilbert space of different codes. And again, you need to choose the right one to recover STEAM. And again, it's not clear what is the recipe to find STEAM in some kind of canonical way. Okay, but now the question is, okay, you have all these logical gates that you can do very easily. What about the distance? So I don't quite know at the moment. It's not completely clear. I want to advertise there's a recent preprint by Kubica and Teixeira, where they kind of construct codes with kind of similar ideas. And they can, in their paper, they really focus on getting code with a certain distance. And they can get codes of distance, whatever, if they use a special kind of groups. But in general, what you can do, you can always write down the Néel-Laflamme conditions if you want to have a code of distance d. So you can write the Néel-Laflamme conditions, and they give you a bunch of equations that you should satisfy if you want to find a code with the right distance. So you just need to find a state phi in the right multiplicity space that satisfies this bunch of equations. And as I was just saying, for the 5-qubit code, there's a kind of canonical choice of phi, and if you do that, I completed that yesterday. The code that you get, it satisfies 90 of the conditions of Néel-Laflamme conditions, but there are 15 that are not satisfied. So it's almost there, but not quite. Okay, so you could say also, okay, for the moment, G was always like a subgroup of SU2, but somehow this group, this construction is kind of agnostic. So you give it a group and it will give you something. So what if you put the group of the whole group SU2? So we know from Neil Laflamme, from Easton Neil, that there shouldn't be a way to find a code with good distance if you do that. And for Bosonic codes, it's kind of clear what happens. So for Bosonic codes, this decomposition is the sum of E-reps. Each E-rep has multiplicity 1. Just means that you have only one code for each E-rep. So there's only a single code that has the right covariance. And this is the dual Rayleigh encoding. So this is the only thing that you get. And this is kind of, at first I was saying, okay, I was thinking that Easton Neil was really because if you take this group, the multiplicity space is just always 1. You have no choice for the code that you get, and you get a bad code. But what about multi-qubit codes? And it turns out that in that case, it's not the same story. So the multiplicity dimension of the 2D E-rep can be very large. It's not 1. In general, it can be very large. It can be exponential in n, in the number of qubits. So it's not just the multiplicity dimension that tells you whether good distance exists or not. There's something more. So if your group is SU2, then the unitary that diagonalizes the representation is well known. It's called the Schur transform. And the reason why it doesn't work, why you cannot correct errors, is basically because with this Schur transform, you can check that if you take an error which is just a sum of single-qubit poly errors, that should be correctable, and this acts trivially in the multiplicity space, so you cannot detect it, and this is why you cannot correct it. Okay, so this was basically what I wanted to say. So in summary, we kind of define this very general formalism to design codes with specific physical representations of logical gates. So in the Bosonic case, you recover GKP CAD codes directly in a very straightforward manner. You can also design new ultimate codes, physical Bosonic codes. For qubit codes, at the moment, it's not clear where to look. If you want to choose to get a code with good distance, it's not clear what's the recipe to do that. As I was saying, maybe I'm kind of optimistic that maybe this exists. There's a recipe to do that. And this formalism is very general. So here I talked about oscillators. So the Bosonic case, I talked about qubits or qubits. But you can put whatever you want for both the logical systems and the physical systems. You can put qubits, oscillators, rotors for both logical and physical systems. You can put any representation that you want for your group. And the formula always works. So there are obviously many questions. The first one is really, is it like a curiosity, or can it be useful? At the moment, I can just recover things that are already known. For qubits, it's not even clear how to recover them if you don't know them in advance. Yeah, the question is really how to find codes with good parameters. It's not clear at the moment. And then, error correction, logical state preparation, I have no clue.
Maybe you said it and I just didn't understand, but in the examples that you present, how do you find the states specifically that give you back these specific codes? Or
you mean for Stein code, for instance?
In your talk, it seems like magic to find.
For the Bosonic codes, yeah, it's magic. You just pick the vacuum and you just pick coherent state and you get the Bosonic codes that you. For Stein code,
that's the first thing you would try.
Yeah.
So okay, and that just happens to work. Yeah. But for these other ones, like
for these other ones, yeah, you need to look.
What does it mean to look? Like, did you come up with a cost function and optimize it, or? No.
Here, so I know what I want. So I know what is for the standard Stein code. I know what is the logical zero state.
Oh, I see.
So basically, the physical state that I input to this thing, the phi, if I input the logical zero of Stein code, then it will give me
I see. Oh, okay.
So that's very easy. So if you know this is the one that you want, it is very easy to find it.
I see. I see. But in general, yeah, I see. Okay.
And you know, it's not clear.
To find a new code, you would need some kind of cost function and then optimize over the
Yeah. So I was saying that for the 5-qubit code, there's a kind of a canonical way to choose phi, and the reason is this. So you see, the multiplicity space of the 2T group here for this rep is C6. It has dimension 6. But now if I look at the multiplicity space of SU2 for 5 qubits, it has dimension 5. And this multiplicity space of SU2, it lives inside the multiplicity space of the other one. So you have something of dimension 5 within something of dimension 6. You know that if you pick anything in the dimension 5 thing, it won't work. So I tried the obvious thing, which was pick something, the orthogonal complement, and it satisfies almost all Neal-Lamb conditions, but not quite.
For what it's worth, the way Ian and Eric do it is they pick these specific groups with very specific reps that are guaranteed to have distance and for any multiplicity. And as a result, there's not a lot of multiplicity. Often, like those particular reps are present for very, very specific parameters and only maybe once in the space. Solving this problem will make this useful.
Can you have exotic operations, like can you put in quantum Fourier transform as part of your symmetry group?
For which one? For the physical representation?
Well,
you can.
Right, ultimately for.
I haven't tried. You can try. I mean, the same formula will work. You put any group. There's no restriction on the group that you can pick. If you pick a group which is too large, you will get something that you cannot compute really.
I guess the group has to be compact.
Okay. It has to be compact because you need this kind of sums. You need these kind of sums to be well defined. So yes, for GKP you have this kind of yes. Yes.
That was really beautiful. Thank you. I'm just curious, maybe you mentioned this and I missed it, but I suppose projective representations would be kind of what you would really need rather than like a representation, because we don't care about the global base. Would that buy you anything at all?
I don't know. I don't know. That's a good point. So usually what we do is the group that we pick, we'll pick it inside SUD. So already we get rid of the global phase like this.
Yeah.
But maybe you get more if you do that. Yeah.
I have a couple of questions. So for like the bosonic codes, like because you're not dealing with like qubits necessarily anymore, and like you can kind of play with whatever. Do you look at any of these like groups that have much more efficient like navigation properties than the Clifford plus C, for example? So like there's like the icosahedrals.
Yeah. So you can do that. Yeah, exactly. Yeah, so it works exactly in the same way. But the Kubichka and Jan Teixeira, they played with that already for qubit codes. Yeah. But yeah, of course, this is something that you can try.
And then my second question is, so suppose I wanted to do this even with like the 2-qubit logical Clifford group. Like you're already talking about 11,000, I think it's like 11,520 elements up to phases. Is that just already at a level where this is going to be impractical? And is there anything you can do with like the fact that these groups often have like nice formal forms that you can maybe leverage or anything?
Probably you want to do that. Okay. Yeah, something I didn't mention is that yes, for instance, for GKP, if you want to recover GKP here, the logical group that you look at is just the poly group you get. But then for GKP, you know that you can do all Clifford operations with Gaussian unitaries. So it's not clear what is the right group to put in. So maybe you would, if you had taken the full Clifford group and put this, and you would have got GKP as well. But turns out that if you just put the poly group, you get GKP already. So it's not clear whether you really need to look at these bigger groups or you can look at smaller subgroups and give you that will give you already. But yeah, that's the scary part. If you these group sizes, they explode very quickly. And yeah, I haven't tried.
Yeah, so you said it had to be compact. Does that basically include the exceptional, the algebra implications of like that kind of compactness too for like 37, 8,
I don't know. Yeah.
Have you tried to use this to find like new stabilizer codes with transversal T?
I haven't, but again, I think, yeah, Kubichka and Teixeira, they have tried that. With similar techniques. I'm not quite sure it's exactly the same technique, but it's. These are non-stabilizer. Which one do you want? Stabilizer or non? Yeah, I haven't tried too much. So there are many things to try, I think.
So if you had like some algorithm in mind where, which like could be more naturally described in terms of some like gate primitives, like, like say a Fourier transform on a d-dimensional system plus some diagonal gates, say. Can you find codes this way that would be better for such algorithms than if you just did the more, I guess, like, the more straightforward way, whereas you say like, let me assume Clifford plus T's, and then get like, this multi-qubit code, and then try to put my algorithm on top of this. I guess could you get like somehow a better code that's more?
Yeah, maybe, but really the question is how do you find the good codes? So you get, with this formalism, you get all the codes that satisfy the conditions that you want. And then really the question that I don't know how to answer in general is how to get the good ones, the ones with good code parameters. The one that will protect against.
Like if like G, I really took that to be like some very specific subset of like my SUVs.
Yeah, but it can be an arbitrary, it doesn't have to be a subset of SUD. It can be any group, say, like a cyclic group, whatever. But you need, and then you need the logical representation on SUD for your logical space, and you need the physical representation in your physical space. But the group itself, it can be, it's an arbitrary for a group.
Okay, let's thank you for the game.
And we will be back at 1:30.